You've probably heard it a million times, right? When it comes to AI, bigger is always better. But what if that's just wrong? What if the real secret to a super smart AI has nothing to do with its size, but everything to do with something way cooler, like the actual shape of its thoughts?
I mean, it's the big question, isn't it? We see these models doing absolutely amazing things, but what's the secret sauce? What's the real difference between an AI that's just okay and one that's a flat-out genius? That's the mystery we're going to dig into today.
Okay, check this out. Picture two AIs. We'll call them Model A and Model B. Model A is just crushing it, 85% accurate, a total rock star. Model B, not so much. It's struggling down at 65%. But here's the crazy part. They have the exact same number of parameters. They're literally the same size. So what gives? What's the secret ingredient that Model A has?
And that right there, that's what researchers call the AI generalization mystery. We're about to bust that old myth that bigger is always better and find out what's really going on under the hood.
And listen, this isn't just some random question. It's a massive deal in the world of AI. Just look at this quote from the paper we're diving into. The author, Sumit Yadav, calls it a fundamental challenge in deep learning theory. Basically, figuring this out would be an absolute game changer for the entire field.
For the longest time, the thinking was pretty simple, More parameters just means a bigger brain, right? It's like giving the AI more knobs and dials to fiddle with. So it should get smarter, learn more complex stuff, and just perform better. It makes sense on the surface. But, as it turns out, that whole idea is kind of broken. And boom, here's the proof. When researchers looked at a whole bunch of large language models and checked the actual correlation between their size and how well they performed, they got this number. R equals 0.07. For anyone who doesn't live and breathe stats, let me translate. That's basically zero, nothing, no connection whatsoever. So the big takeaway here, size is not the answer, not even close.
All right, so if size is a dead end, then what's the real answer? Well, this is where things get really, really interesting. The big idea in this research is that the secret isn't size, it's shape. We're talking about the geometry of the AI's internal world, the literal structure of its digital thoughts. Let's break down what that even means.
Okay, first up is a term called output effective dimension. Don't let the name scare you. The best way to think about it is like the resolution of a picture. You know how a low-res image is all blurry and you can't see much detail? That's a low effective dimension. It can only hold a simple idea. But a super sharp, high-res photo, that's a high effective dimension. It can pack in tons of rich, complex details all at once. It's about how much nuance the AI's mind can hold.
The second big idea is total compression. And this one is all about the journey information takes inside the AI. Imagine the AI gets hit with this messy flood of raw data. Total compression measures how good it is at sifting through all that noise and distilling it, compressing it down to its pure essential core concept. It's a measure of how efficiently the AI thinks.
So let's walk through this journey of an idea. First, you've got the raw input. Think of all the pixels in a photo. It's super complex, kind of chaotic. Then, the AI's network goes to work, layer by layer. It starts transforming that data, refining it, compressing it. And what comes out the other end isn't just a label like cat. It's a really rich, well-structured idea, a geometric shape, really, that perfectly captures the essence of what it just saw.
Okay, so this whole geometry thing sounds pretty cool, right? It's a nice theory, but does it actually work? Is there any proof? Let's see what the data says.
Whoa! Okay, look at this. The trend is just crystal clear. On the bottom, you have total compression. The further left you go, the more the AI is squishing down the data. And on the side, you have accuracy. Just look at that line across all 52 of these models. It's a perfect downward slope. The takeaway? The models that compress information the most are consistently the most accurate. It's right there in the data.
Okay, but this next part? This is the mic drop moment of the whole study. The researchers did something really smart. They basically asked, what if we could ignore size completely? Let's pretend every model is the same size and just look at the link between its internal shape and its performance. When they did that, the correlation between that output effective dimension we talked about and accuracy was 0.75. That is huge. It's an insanely strong connection, way more predictive than model size ever was.
And this chart just hammers that point home. See the light bars? That's the simple correlation. But the dark bars, that's the magic.
That's the correlation after you remove the effect of size. And look, for our geometry metrics, the predictive power actually goes up. This is definitive proof. This shape thing isn't just a stand-in for a bigger model. It's telling us something completely new, something size can't.
Okay, so this is where every good scientist asks, is this just a coincidence, or is it actually causing the good performance? To find out, they ran a test. First, they messed up the geometry on purpose. They injected a bunch of random noise into the AI's thoughts. And guess what? Accuracy totally tanked, like a negative 0.94 correlation. That's a near-perfect negative relationship. Then, they did the opposite. They used a clever trick to clean up the geometry, to remove the noise. And incredibly, the accuracy stayed almost exactly the same. This is huge. It proves it's not just a correlation. Better geometry causes better performance.
So, everything we've talked about so far has been with vision models, AIs that look at pictures. But the big question is, does this whole geometry thing work for language models too? And you know what? It does, but with a really cool twist.
So it turns out there are kind of two families of language models. You've got encoders like BERT. Their job is to read text and understand it, to classify it. And they work just like the vision models. They compress information to find the core meaning. The more they compress, the better they are. But then you have decoders like GPT-2. Their job is totally different. They have to create text, predict the next word. To do that, they have to do the exact opposite. They need to expand their internal thought into the huge space of all possible words. So for them, more expansion is better.
So at first, this seems like a contradiction, right? One compresses, the other expands. But it all comes together in this one beautiful, unified idea. It doesn't matter which direction the transformation goes. What really matters is the magnitude of the change. A great AI is one that can dramatically reshape information, whether that means shrinking it down to its essence or blowing it up into a world of possibilities. So, let's zoom out. What does all this actually mean for the future of AI? Because this isn't just some neat finding for a research paper. This could fundamentally change how we think about, how we test, and even how we build AI from the ground up. All right, let's do a quick recap of the big takeaways here. 1. The shape of an AI's thinking matters way more than its size. 2. We can actually measure this shape with things like output effective dimension and total compression. 3. This isn't just for images, it works for language models too. 4. And this one is a real game changer. You can measure all this stuff without any labeled data. That's a huge shortcut for developers. And 5, we know this isn't just a random correlation, it's causal. Better shape means better AI, period.
So what's the most powerful thing we can do with this? Well, we can now look inside an AI while it's still training and see if it's developing good thoughts. We can tell if a model is on the path to becoming a genius long before we spend millions of dollars finishing its training. That could save an incredible amount of time and energy. It's kind of like being able to tell if a student is going to ace their final exam just by looking at how they organize their notes in the very first week of school. It's a peek into their potential.
And that leaves us with one last mind-bending question to chew on. For the very first time, we have a real, measurable connection between something as abstract as geometry and something as complex as intelligence. So, if we can now measure the shape of a thought, does that mean that one day we could actually design perfect intelligence from the ground up? Not just by building bigger and bigger models, but by carefully engineering the perfect geometric shape for a thought, right from the very start?